Now that we're going to look at the process of a liquid changing into a gas, right? Even without the boiling point, like what happens to water that we take from the sea and keep outside, spread it out, and get salt from it. Now, the first thing we want you to observe is by asking a lot of questions. One of them is, why do we spread out our clothes when we dry them? Yeah, you put them onto the rope and then you spread them out. You don't crumple them together. Why? They dry a lot faster on a sunny day, right? Before all this, how do clothes even dry? I don't know, right? So a couple of questions like these, and even questions like, if you keep a bowl of water, after a while, it reduces. All this happens, even though we know that water is clearly not reaching its boiling point. And when you dry a cloth, what is happening is that water is basically what's called evaporating, right? Water is evaporating, which is a process in which water or any liquid changes into the gaseous state before the boiling point is achieved. Now, without going into so much jargon, which I've been going into till now, let's try and visualize a liquid in a completely different manner, right? Let's take a liquid, instead of imagining it as we usually do, let's imagine it as a large number of little balls, right? Some of them, it's not so calm, it's like people are running around and little dolphins, jumping up and landing back inside, almost like dolphins. If it's a surface, it's like something jumping up and landing down, jumping up and landing down, and so on and so forth. Then, what we need to understand is that overall the temperature of this liquid could be less than its boiling point. But one of these dolphins might just end up getting enough energy, right? Because there are so many collisions happening inside. Right? One's hitting the other, some of them suddenly end up getting a kinetic energy enough to be able to break away. And if this continues to happen for quite some time, what you would notice that the one that broke away has broken away, right? It's not part of the water. In other words, water is drying, right? It's becoming gaseous, water vapor. Water with enough kinetic energy becomes water vapor. Now, with this picture in mind, what all could aid this, right? I could have electromagnetic radiation. Whoa. In other words, light, right? From the sun usually. And that's one of the reasons why sun dries clothes faster. Now, how could sun help drying clothes faster, right? Sun's going to hit light rays, right? And one of those light rays is going to bounce onto this, or it's going to hit onto one of these water molecules, thereby giving it enough kinetic energy, which is called a photon, right? So a photon comes across, hits one of these molecules, gives it enough energy, escapes, right? Helps evaporation. Great. Now, obviously, the larger I make the surface, the more of them can escape, right? Because it's clearly a surface phenomenon. Nobody from down there, no matter how much kinetic energy they have, can escape. The only thing they can do is transfer it to somebody above and hope that it reaches somebody on the surface, and then they escape, right? Now, let's also ask, how could wind affect this? On a windy day, clothes dry faster, if you haven't observed it already. How could that be? Watch what happens as a molecule of wind comes across and a dolphin's jumping, right? And the dolphin here is the water molecule. Hits it, gives it enough kinetic energy for it to escape away again. Great. So what we observe here is the surface area matters. Temperature, right? Yeah, matters, because the larger, if you have some kind of radiation, the sun, it's going to start giving kinetic energy. How could the temperature matter? The larger the temperature of the air, more molecules of the air are very, very energetic, which means one of those collisions with water is going to help give enough kinetic energy for it to escape. Great. Now, what about this thing called humidity? Right? Because the last thing we saw that helps it, right? We saw the radiation helps it, the temperature helps it, the surface area helps it, wind helps it, right? Wind is, in other words, also kinetic energy of the air molecules. Great. So, what does humidity do? And what is humidity in the first place? The amount of water molecules already present in the air. Now, why is that important? Why is that even part of our equation? It is part of our equation, or is part of our system here, because just like some dolphins can leave, some of those dolphins that already escaped, which are in the air called humidity, might end up finding their way back into the water just randomly, right? Some people are leaving, some people are entering. So the larger this humidity, what does that mean? More of them can come back, which means effectively the evaporation is going to reduce, right? So in one sense, what does humidity do? It reduces the effective evaporation, because just like some of these guys can escape with larger kinetic energy, some of them can start losing some, land back where they started from. Or even if they came from somewhere else, they could just land back over here, thereby the gas becomes, or the vapor becomes water. So humidity negatively affects it. Interesting, right? Now, the biggest question is, how does this create cooling? Because we know that's why we sweat, by the way, right? So if you sweat, it evaporates and then you feel cool. Yeah. So what happens is, just logically speaking, let's not go into the terms of it, just logically speaking, right? What is your temperature? The amount of kinetic energy that you have, right? So let's say there are 10 molecules out here. The average is, say, 5. One of them with a higher kinetic energy left, right? What does that mean? Somebody took away some of the kinetic energy, leaving behind lower kinetic energy. So just by the process of evaporation, what does that mean? People with higher kinetic energies are leaving. Yeah, it's like the brain drain of India, right? Smarter people leave, country becomes stupid. Higher kinetic energy leaves, what's remaining is lower kinetic energy, or in other words, lower temperature. What we feel is cooling, right? Lower temperature is what we feel as cooling. Yeah, this is called the latent heat of vaporization. Now, this is one of the reasons why people sprinkle water on a sunny day, because water has a very high latent heat of vaporization. When it evaporates, it leaves behind the surface being pretty cool. Now, this is one of the reasons why we must wear cotton clothes during summer. Yeah. And also, have you ever noticed that you keep something very, very cold, bottle of water, right, on the table. It appears as if it's sweating all of a sudden. Where is that water coming from, right? The water from inside didn't escape to the outside. So where must that water be coming from? Now, clearly, that shows that the larger the humidity, the more that will happen. Because more molecules of air in the air, more molecules of water, right, water vapor, are roaming around. And when they hit this bottle of water, they lose energy, right, because it's very cold. They lose energy and condense onto the bottle of water, eventually forming all around it, right? Now, these are interesting applications of either evaporation and condensation, which are pretty much the two sides of the same coin. And with this, we kind of put our final wrapper around what we've understood till now, which is the states of matter, right? Matter around us. So as an overall run, what did we see? Matter is made up of particles, and they're very, very small. They have space between them, move around a lot, and attract each other. They exist in 3 major states. We're going to add 2 more in some time. Solids, liquids, and gases, with a smooth transition between them. And we can use temperature and pressure to vary or take objects or substances from one state to the other. Great. And finally, we saw that even without temperature or pressure, we can change the state by a process called evaporation, and the inverse process called condensation, where they lose energy and come back inside. Now, the last bonus section of this is that the states of matter do not end with the 3 states alone. There are 2 high-level states called plasma and BEC, or Bose-Einstein condensate, which we'll not go into too deeply, except that plasma is a very, very high temperature state where the gases are completely ionized. One of the places where it is existing is the core of the sun. Right? The core of the sun has nuclear fusion happening at extremely high temperature, and things are existing in the plasma state. And about the Bose-Einstein condensate, we really encourage you to go and find out more about it. And with this, we're going to let you jump into our next module, which is the next chapter itself, where we question the purity of the things that you see around you. So we'll see you there. It's already queued up for you.